Welcome back. Sometimes we have data where there appears to be a correlation between two different parameters. For instance, a trend over time. And sometimes we have an idea of what this correlation is, what we would call a model. If we can express that model using mathematical equations, then we can attempt to fit those equations to our data, either in order to test how good our model is or to demonstrate that it is good. This is something that could be a very powerful way of storytelling with data, and so let's have a look at how to do it in Veusz. We're going to be looking at the median housing price over time, starting in 1963 and going to 2020. Here we have the initial price, by which we mean the median price of a house at the start of that year. This has already been imported into Veusz, so if we want to make a plot of this, let's go ahead and insert graph, a scatter widget, and then say year and initial price. This plots this with all these points here, which I think is a little bit hard to see, so let's go ahead and just turn on our line fit and get rid of our markers, so that I just have this line over time. This is our data, and red does stand out, but I'm just going to make our lives a little bit easier and say that this line should be black. That's going to let us see things a little bit better as we move along. So this is our data. We could, of course, make this look better. We could add titles to both the Y and the X and beauty it up, but that's not what we're really interested in. So let's just go into fitting. We could fit the data as I've shown here, but I think it's going to be easier for us to actually modify the data ever so slightly and go back and say year since start. For some of the equations we're going to be using, it's just going to simplify things for us to do it this way. So let's start at 0, 1, 2, and 3, and so on. And so we can highlight all of this and then propagate that trend down. Hit save, and then go back to Veusz, refresh, and then now we're going to plot our data along year since start instead. So we're starting at 0 and going through about 60 years worth of housing prices. Again, this will make it a little bit easier for us to see the fits and come up with the equations that we need. So now we want to fit this data. What do? In Veusz, we use the Fitting widget. Clicking on this brings up a new properties window. I have a button that says Fit Function. We're not quite ready to do that yet. A place where we can define the function that we want to fit, which here is a line, and let's just start there. And then the adjustable parameters for that function, which is A, in this case, our intercept, and B, this case, our slope, with respect to X, the X-axis, and that is specified down here where we say the X-axis is X and the Y-axis is Y, referring to the X and Y-axis widgets up here. Then I can say the data I would like to fit is year since start on the X and initial price on the Y. When I press fit function, it will fit that function to the data. So let's see that. This blue line is now our fit. There's a few things you might notice about this. For instance, it looks a little too flat. Like, why isn't it fitting up here? And this is a quirk of Veusz whose default is to fit data using a weighted fit that accounts for the error in the data. If you don't supply error in the data, it just gives an error of like 10% to each point. The problem is when you have data like this, which has low values and then high values, it looks like there's much more error up here because it multiplies these large values by 10% and these by 10%. And so you have tighter error here, and then we favor a fit down here. In cases where we have error, this is not a problem. But in cases where we don't, like right now, we need to use a hack to get around it. And so what we're going to do is we're going to insert a new column here next to our price. And in Veusz, how you say that I have symmetrical error for these values is to the right, put in a column that's headed with plus minus. Now, if you try to do this in Excel and just hit enter, you'll get an error because it thinks you're trying to use a formula. So I always put a space at the front, and then it doesn't have this issue. It doesn't really matter what we pick for the error as long as it's all the same and not 0. And so let's go ahead, we could assign these 1 and then propagate this all the way down. And now when Veusz looks at this, what it will think is that we have a price with an error of 1 for everything. That's uniform error. So I'm going to go ahead and save that. I'm going to go back to Veusz. I'm going to copy this. And then when I refit this, you'll see the line changes because it's accounting for even error all the way down, and we'll get something that looks a little bit more reasonable. That's maybe what we'd expect. Now, it's not really a great fit for a number of reasons. One, this data starts above the line, goes below the line, and then goes up above the line again, suggesting that overall it's curved. In addition, this fit gives us a model that predicts negative house prices back where we started, which is clearly wrong as well. So we'd like to have a model that's somehow curved. And there's a lot of different ones that we could use, but one of the ones that I think is rather common would be an exponential fit. So let's call the one we've just fit linear. And let's make a new widget called fit1, but which we will call exponential. We need to give it an exponential function. It's basically going to be an upward curve that's an exponential plus some offset here, which looks to be about $25,000 if I'm looking at where this crosses the line. We use Python notation, and so I think about an exponential as exp, that's what it is in Python. Between two parentheses is everything that goes up in that exponential. It would be something like a constant times x. We could use b if we want, but we can also give it a name, like tau, the Greek letter, and that's also fine. We need to scale how much of this exponential there is. We'll use a factor a, and then add in that constant that's an offset here. If I click here, you'll see it gives us an error, both here and down here, and basically it's saying I can't evaluate this expression because you haven't told me what tau is, or actually what c is, or what a is, but tau is just the one it saw first. So we need to also give us values for this. So let's start with tau. Let's say that is 1, just as an initial guess. Let's say a is also 1, and c we said was probably something like 25,000. Now if I click off of this, it will evaluate it. And you can see that we start at about the right place, but this curvature is like really sharp. Probably far too sharp. So what if this was instead 0.1? Now you can see it's flattened it out, but maybe a little bit too much. So maybe it wasn't so much that the curvature was the problem, but it was the a term. So what if this a term is 0.1? And then you're starting to see how this behaves. Now we could play around with this until we get something that looks like it's kind of a good approximation, but most of the time, if I just say fit function, it'll find what it should be anyway. Isn't that the whole point? You'll see that when I clicked fit function, it's telling me I can't fit, and it throws an error down here in the console. The console is saying none type, object has no attribute data. And the reason is that we haven't set the x data to something reasonable. We need to tell it that it's the year since start, and that the y is the initial price. Now when I press fit function, it will try to fit it. It doesn't look great, and one of the things that Veusz does is it like iterates, starting at a particular residual and going until we've reduced it by a certain fraction. And so I have a slightly better fit, but not a great fit. And I can just keep pressing this fit button, and we'll see that it keeps refining this fit until I get something where it doesn't look like it changed. We can look at the results, which are shown here, A, C, and if I scroll down, tau. I can also see that written here in the output expression, where I scroll over or widen this, and I can see that it's giving me the exponential, the value for tau that I ended up with, the value for a that I ended up with, and then plus a negative c term here. These values are also displayed in the console, so every time I hit fit, it gives me these fit results here, which are a is this value, c is this value, and tau is this value. And then it also gives me estimates of what it thinks its standard error is from that fit. It also gives me goodness of fit parameters, chi and reduced chi-squared, which we'll talk about later. I could also see those here where I have fit chi-squared and fit reduced chi-squared. Other things that I could change are the min range and the max range that I want to fit. So let's say that going back to this data for some reason, I didn't want to fit the entire range but wanted to start at year 10. I would just put that in as year 10, and then you can see it doesn't draw this full line, and when I hit fit, it will give me a slightly different fit that's ignoring the data over here. That's not what I want, so let's just go back and say the fit range, the minimum is 0, that would work, or I could say auto, and it will just, when I say auto, use all the data that it can. And so I fit function and it goes back. This is a slightly better fit, right? It runs through the points. It also doesn't go negative. It fits a little bit more tightly to all of these lines. How do we know it's a better fit? That's something we'll talk about again in the class. Now let's think about this line and how we might format it. We have all the same control we normally expect. Like here's the line and I could choose to change its color somehow. So maybe I don't like this green, but I want dark magenta. Fine, I got it. I can change its width, its style, its transparency. I could fill below this line. I could fill above this line. Here I can also choose to hide the line. But now I have a new thing that says steps. And what is this? Well, it's telling me how many points along this axis I want to draw. Yours probably defaulted to something like 100 or 500. I could put it as low as 10. And what you'll see is that like these lines, there's like chunks and sharp points in the line. Let's go all the way down to 3. 1 point here, 1 point here, and 1 point here that are connected by straight lines. And so when you type in steps, you're saying how many different points are we actually calculating and for our fit. And I'll say 1,000 because I think that always looks smooth, basically no matter what you're plotting. Every now and again, that might cause you problems, but that's the default that I use. Okay, so then what could we do? Could we find a better fit? Well, we are talking about financial things, and sometimes when we think about financial things, we think about compounding interest. And so we could try another fit where we have compounding interest. We'd have to look up the equation, but here it is. And so let's see if we can translate that equation somehow into something that views will be able to fit. So let's go ahead and move this views window over a little bit so that I can see what's going on. And for some reason my computer's having trouble. I don't know why, but that's okay. We'll add in a new fit parameter or new fit function, and we'll just type this in. This is the amount. We need P as the principal, 1 plus R, which is the interest rate, over N, which is the number of times it's compounded per unit T. So let's just assume that this is going to compound once per year. And then I have N times T. So that's a pretty easy one to translate. I have P times 1 plus R divided by N raised to the power of, and when we have raised to the power of in Python, it's a double asterisk. And then I'll have N times T. Now we said we're going to assume this compounded just once per year, so actually all these N's are just going to be 1s, and all we have left is a P and a T. That P is probably close to what our y-intercept was, so 25,000. And then R, I don't know, let's just set this to 1. And then say we want to fit this to years since start and initial price. So let's go back then. And then what we will do is I'll say fit function. It's telling me that only finite values are allowed, which basically means it was unable to find a good fit with the parameters that I started with. So let's try this again. How about 25,000? And instead of an interest rate of 1%, which might be too much, let's just say it's an interest rate of 0 and see what that looks like. It's also telling me that the reason I can't fit this is because I used T. I was reading that equation and not thinking that it needed to be X. So how about this? Now I have a flat line because there's no interest rate. If I set this to 1, you can see that it was pretty high. So how about an interest rate of 0.1? And let's see what that looks like. Pretty good. Let's hit fit. And there it is. I have this light purple. That's a little hard to see. So instead of light purple, maybe we can have it be orange. You can, to me, this looks not quite as good as our exponential function, which is the purple one, better than the blue. So our linear is right out, and I'll say hide And then this here was our compounding interest. Now, one of the reasons this might not fit, you might think, is that, well, we said it compounded once per year. But how do we know that's true? Didn't the equation have an in it? And you're right, it certainly did. If I go back and look, you'll see that we've just made that an unadjustable parameter that we thought was 1. So let's add that back in. We'll just say that this is in, and this is in here. And then I need to give this that parameter as well, so I'll go in equals 1. That's going to be our initial guess, and then I'll let this float, and we'll see what happens. I fit it, and you'll see that the fit value did give me a 1 or an in that's very close to 1. And so it turns out that the compounding portion of this wasn't the problem. It just doesn't quite describe the housing prices as well as this exponential growth here. Okay, so at this point we know how to fit equations to data. We don't quite yet know how to explicitly tell whether something's a better fit or not, and that's something we can talk about later, and it comes from thinking about the chi-squared in part. However, at least we know how to take a model as a guess, fit it to our data, and then think about whether we think it is a reasonable description of what's going on. If it is, we can leave that line on there and tell a pretty nice story.